Alright, so welcome back to all the NEET aspirants. In this video, we'll be continuing with our unit of units and measurement. Okay, guys, so we are here to prepare for NEET 2024, and I am Dr. Shankar Sir, your physics educator. So, in the last session, guys, we have started with the units and measurement, and we have seen a lot of things. Okay, like what are the fundamental quantities, what are the derived quantities, what are the supplementary quantities. Okay, and in the last session, lastly, I told you that supplementary quantities are the only quantities which has units but no dimension. Okay, now in this session I am going to tell you what is dimension and what are the dimensions of various physical quantities. Okay, so in physics we have so many physical quantities, and as we know these physical quantities are the ones, as we know, these physical quantities are the ones which are the language to understand this physical world better. That is the language given to us by various mathematicians, various scientists. Okay. So in this session, we'll be talking about the dimensions of various physical quantities. And the students who haven't seen the last video, please go and watch that video as well, because this video is going to be in continuation of that video. Okay. So this is video number 2, session number 2 for the chapter of units and measurement. Okay, so guys, my name is Dr. Shankar Tripathi, as I told you, and in the last session we have discussed about all this. So let me come to the point directly. So in the last session we have been talking about the dimensions. Okay, now what is the dimensions? Okay, so before we come to the dimension, let me give. So in the last session we have seen some fundamental physical quantities, right? So these fundamental physical quantities, let us give some representation to them. Okay, for ease of understanding. So basically the fundamental quantities were, so we had the length, we had the mass, we had the time. What else? We had the temperature. Okay, we had the temperature, we had the current, that is the electric current. Okay, we had the what? Intensity, that is the luminous intensity. And we know luminous intensity is used to what? It is used to represent the energy of light. And finally we had the amount of substance. Okay, now to get the dimension of something, first let us give some representation to these, that is the fundamental quantities like the length, mass, temperature, electric current, etc. Okay, okay, so now in this case what is going to happen? So this length, let me represent it like this. So this is going to be L, like this. What is going to be the mass? It is going to be M, like this. What is be the time? We'll be representing it like T. What will be the temperature? So what was the unit of temperature? It was Kelvin. So sometimes it is represented in Kelvin or it is represented in theta. Okay, like this. Okay, then we have the electric current. So what is the unit of this electric current? What is the unit of this electric current? So the unit of the electric current is ampere. So normally the electric current is represented like this, A, or like this, I. Okay, okay, so see, sometimes what happens, like in a formula we have electric current, we have some constant, that is K also. Now in that case, what happens? We do what? In that case, what we do? In that case, we represent it by either of the notation. If some constant is there, and the constant is represented by A and the current is involved, so you will be rather representing it by I for ease of your own understanding, right? Ease of your own understanding. Okay, Now, similarly, this luminance intensity, what was the unit? The unit was candela. So we represent it like C, and the amount of substance we represent it like mole. Okay, so in this chapter of units and measurement, when we'll be talking about the dimensions, the first thing that we need to understand is, first thing we need to do is we need to give some representation. We need to give some representation to these. Okay, to what? To the fundamental quantities, because as we learned, all the derived quantities are in a way represented in terms of fundamental quantities. So, sir, are these are dimensions? These are dimension? No, these are not dimension. These are not dimension. These are just the representations of the fundamental quantity. These are not dimension. Students often confuse. They said this is the dimension. No, 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 this is not the dimension. Please understand this. The dimension. What is the dimension then? So I'll define the dimension for you. So we can define dimensions. So we can write dimensions are the power. Dimension are the power. Okay, so I hope you understand what is the meaning of power. No, this is not work per unit time. This is not that power. This is the power to which the fundamental quantities are raised. So I am talking about like, so 5 to the power 6. So this is the power we are talking about here, not the power of that power of the physics for work in upon time. I am not talking about that. So dimensions are the powers to which dimensions are the power to which dimensions are the power to which the fundamental units, the fundamental units are raised are raised in order to express any physical quantity. So physical quantity is what? It is the PQ. We remember that, right? Okay, so dimensions are the power. Please understand this. I'm repeating it again and again because I want it to be in your mind and you must remember it by your heart. Dimensions are the powers to which the fundamental quantities are raised to express any physical quantity. Okay, so let me name a physical quantity. You will be able to get it. So see, lot of questions you will see in the previous year of NEET questions are from this particular part. So basically, this session is going to ensure you at least one question. Okay, or probably one question will be asked in the NEET 2024. So definitely this session is going to be very important for you guys. So let me name any physical quantity. So can I say area is a physical quantity? Okay, area is a physical quantity. So absolutely the area is a physical quantity. Now, area is the physical quantity. How can you represent the area in terms of fundamental quantities? So we are going to use these fundamental representations, fundamental quantities to express any quantity from now onwards. Okay, so area is what? Area is, what is the unit? Meter square. So we can write it like this now, L cross L. So in terms of fundamental dimensions, or fundamental units, we can represent it like this. Now, can I write this area is equal to L square? Okay, can I write it like this? So obviously, sir, you can write it like this. Now, what is the dimension of the area? Now, if I ask you what is the dimension of the area, what shall be your answer? So the live student can respond to me on this. Any live student who want to answer me? What is the dimension of area? Now, when I ask this question, what is the dimension of area? Many students say, sir, L square is the dimension of area. So guys, this is not the dimension. Remember, the dimensions are the powers to which fundamental units are raised. Okay, so these are the powers to which fundamental units are raised. So L square is not your dimension. Okay, now again, let me ask you this question. Sir, what is the dimension of area? Now, you must say, sir, your question is in a way wrong. What is wrong? What is wrong in my question? So the question must be, what is the dimension of area in the fundamental unit of length? This shall be the exact question. Okay. Okay. What shall be the question? The question shall be, what is the dimension? What is the dimension of area in length? Okay. What is the dimension of area in length? So the dimension of area in length is 2. Okay, because dimensions are the powers to which the fundamental units are raised to express any physical quantity. Okay, so for area, the dimension of area in length is 2. Okay, so when the dimension is asked, it is also important to know that the dimension is asked of what fundamental quantity. The dimension is asked of what fundamental quantity. So if I ask, okay, so now please understand this. So we can represent the area like L square. Now can we represent it like this also, sir? M0, because there is no unit of mass. So you can do it from the formula or from the unit. So the unit we know is meter square. So basically the fundamental unit of length is used twice. Okay. Now if I ask you, can I represent it like this also, sir? M T or M L square, M L square T0, M L square T0, right? Yes or no? Yeah. Sorry. So what is the dimension of area in length? So what is the dimension of area in length? The dimension of area in length is 2. I was talking about this. Now please understand this. Can I write or I represent the area in terms of fundamental units like this? M0, L2 and T0. Can I do this? Can I do it like this? Please answer me. Can I do it like this? So definitely, sir, we can write it like this as well. Okay. So why not we have used temperature? So we could have written it like this also, no? So temperature K0. Okay. We could write it like this if current in terms of current, that is A0. So we generally don't do that. Okay. Generally, a physical quantity related to the first part, that is mechanics. Okay, normally we represent it in terms of m, l and t. Okay, so there is nothing wrong if you represent any physical quantity in terms of all seven, in terms of all seven fundamental units. There is nothing wrong to it, but in general we represent a physical quantity in mlt, that is mass, length and time. Okay. Okay, so certainly I can write this area like m0 l square t0. Now I am asking you, what is the dimension of area? Now don't say, sir, m0 l2 t0. This is not the dimension, because dimension are the powers. I think this must be in your mind now. Dimensions are the powers to which the fundamental units are raised to express any physical quantity. Okay, now sir, your question is again wrong, because you didn't mention that what is the dimension of area in m or t or any other fundamental unit. Okay, now the question should be, if I ask you what is the dimension of area, what is the dimension, what is the dimension of area, what is the dimension of area in mass? So what is going to be the dimension of area in mass? What is going to be the dimension of area in mass? So you may say that the dimension of area in mass is going to be 0. It is going to be 0, right? Now what is the dimension of area in time? So sir, it is again going to be 0. Okay, now, if further I ask you that what is the dimension of area in intensity of light or luminous intensity, what is the dimension of area in luminous intensity? Again, it is 0. Okay, so area have dimension only in length. In any other fundamental unit, it has no further dimension. Right now, if I ask you, what is the fundamental, let us take one more example. So what is the dimension of velocity in mass, length, and time? How would you answer it? What is the dimension of velocity? What is the dimension of velocity in mass, length, and time? So what is the dimension of velocity? So for that, you must know the formula of velocity, or you must know the unit of velocity. Okay, so if you know any one or both of it, then it is absolutely fine. But if you know any one of it, you can find the dimensions of that particular physical quantity. So velocity, what is velocity? So it is change in displacement upon change in time. Let it be displacement upon time. No worries. Okay. Okay. Displacement upon time. Displacement upon time. So what is going to be the unit to it? This is going to be meter per second. So you can use either of it. Okay, so how can we represent the velocity in terms of dimension? So for displacement, it is a length. For time, it is t. For time, it is t. So basically, the fundamental dimension of velocity. So if I represent it in fundamental units, it will be c. There is no dimension to m. There is no unit of this mass, so we can write m0. L is 1, and t, it is in denominator, so it goes in the numerator. It would become -1. Okay. Now again, if I ask you what is the dimension of velocity in mass, what would be your answer? What is the dimension of velocity in mass? So dimension of velocity in mass, dimension of velocity in mass. Okay, dimension of velocity in mass. So this is going to be what? It is going to be 0. What is the dimension of velocity in length? It is going to be what? It is going to be 1. What is the dimension of time? What is the dimension of velocity in time? Okay, so this is going to be -1. So basically, guys, and why finding out dimensions is important? Because see, using these dimensions, we can further check the correctness of an equation. Okay. So why this dimension analysis is important? Why this chapter is important in context of this overall world of the physics, where it is helping us. So basically, when we are good at dimensional analysis, we can check to some extent. Okay, on a basic level, I may say. Okay, not on very high level. To some basic level, we can check the correctness of equation. Okay, to some extent, to some level, we can even form the formula. See how interesting it is. Okay, so when so like the Newton has given some law, he has given some formula. Like any other big scientist have given some formula. You also can give some formula using the dimensional analysis, that the use of by using the dimensions, right? Okay, so it is having big use. But first of all, we must understand to find the dimensions. So again, the dimensions are the powers to which a fundamental unit is raised to express any derived unit or derived quantity, right? Okay. Now, in the same way, we can find the dimensions of many quantities, many quantities. Okay. And lastly, I was talking about the angle. Okay, angle. So, what is the unit of angle? Angle unit is radian. Okay, so for angle, plane angle, the unit is radian. Now, if you want to represent it in terms of fundamental units, so there is no fundamental unit there. Okay, in radian, you can't express it in any of these fundamental units. So, if you want to represent it in terms of mass, length, time, what is the power you are going to give them? So, sir, obviously, we are going to give them the power of 0. Okay, so if all the fundamental units have 0 power, that means such quantity is dimensionless. Okay, so radian and steradian, although they are units, but they are dimensionless. So at this point, we left the last session. Or if you remember, the supplementary quantities are those quantities which have units but no dimension, and these are the only physical quantities which have the units but no dimension. Okay. Okay. So radian is steradian. Okay. For solid angle, we know the unit is stay radian. Okay, stay radian. So radian and stay radian units have no dimension. Okay, okay. So one point is this important. Now, what will be the dimension of, let's say, so I have a number. Let's say the number is 5. Okay, the number is 5. What is going to be the dimension of this 5? Okay, so you are again going to say, so these are what? These are dimensionless. Okay, we have spoken about it in the last session, or any student who haven't watched the last session and watching this session, I request them to watch that last session as well. Okay, so then only you will understand all the concept in a good way. Okay, now if I say we have a number, we have a numeric value that is maybe 5, 10, 100, 1000, anything for that matter. Now what is going to be the dimension of it? So again, sir, this is a constant. This is not having any dimension. So this is also going to be dimensionless. This is also going to be dimensionless. Okay. Okay. So now numbers are dimensionless. All the constants are not dimensionless. Please understand it. Okay. There are a lot of things about it there. So every point you must listen. See, numbers are dimensionless. Remember, not all the constants are dimensionless. Okay, like for example, constant of gravitation. Okay, so constant of gravitation has some dimension. Okay, okay. Planck's constant have some dimensions, right? Stephen Boltzmann constant. Okay, so these constants, there are constants in the study of physics which has dimensions. Okay, though they are constant, but they are not dimensionless. So numbers are dimensionless. Some constant are dimensionless, like refractive index. Okay, okay, that is a dimensionless constant. So some, basically the constants which do not have unit. Okay, okay. So why number is dimensionless? Because no number has some unit. Okay, this is a numerical value. So the constants, remember the constants which do not have units, are dimensionless, are dimensionless. Okay, okay. Now what we are going to do, so see, there are so many chapters in this physics subject. Okay, okay. And in each of the chapter you are going to counter many of the physical quantities. So we are going now to develop the dimensions of these physical quantities one by one. So I'll try. So there are hundreds of physical quantities, hundreds of derived quantities. Now we are going to mention some of here, okay, so that you can be able to use them in the future chapters also. And so many questions are coming from this part. So from NEET previous year question, if you see, you will find the question like, okay, what is the dimension of force? Okay, what is the dimension of Planck's constant? Okay, what is the dimension of dynamic coefficient of viscosity? Okay, okay. So all these questions are asked to you. Okay, so what we are going to do now, we are going to find the dimensions of various physical quantities. Okay, dimensions of various physical quantities. So we are going to go by one. So the live student can suggest me also at times that what physical quantity you want to find the dimension of. So let me start with some basics. So area we already have that. Okay, so you can do by the unit. If you know the unit also, if you know the formula, you can go by that. So what is the unit? Unit is meter square. So what is going to be the dimension? In the form of dimension, you can write it like m0, okay, L square T0, right? Okay, so normally we represent the dimensions in terms of mass, length and time. Though, as I said, you can represent it in all the fundamental units. Okay, now second thing could be volume, right? So what is the dimension of volume? The live student can quickly tell me. Okay, so what is the dimension of volume? So all of you must be approaching with me. Okay, so those who are watching this video, who are watching, if you are watching it recorded form, okay, what you have to do, you have to pause it here. Okay, okay. So before I get you the dimension of volume, you must firstly do it in your copy. Okay, this is the dimension of the volume. So in this way guys, you will see that the amount of revision and the question solving you require will be reduced. Okay, it is going to be reduced to some extent, to some level. Okay, so volume, what is the unit of it? It is meter cube. So can I represent it like this? M0 L cube 30 T0. Okay. Okay. Now I'm not going to write it, but if I ask you what is the dimension of volume, don't you ever say M0 L3 T0. You must say that the dimension of volume is 0 in mass, the dimension of volume is 3 in length, the dimension of volume is 0 in T. Okay. Okay. Now similarly, we have this mass density. We have so many mass density. Okay. Sometimes you call it as a specific mass also. So what is the, so we represent it like this, see, rho. Okay, this is the general representation of this mass density. Okay, so this mass density, what is the formula to it? So sir, it is mass per unit volume. Okay, so what is the unit of this mass? So the mass unit is kg. What is the unit of this volume? The volume unit is meter cube. Okay, volume unit is meter cube. So what is the unit of this mass density? Kg per meter cube. So this is going to be m. So for kg it is m1. For meter cube you can write it as l cube. Okay, in the denominator. So we can further write it like this, m1. Okay, okay, l minus 3. Okay, and T0. So with practice right away, just by seeing the quantity, if you know the formula or you know the unit, okay, you are going to get me the dimension just in a snap, right? Okay, now moving ahead. So after mass density, can you suggest some more units? So velocity, speed. Okay, velocity. What is the unit of velocity? So we just have done it. So mass, sorry, distance per unit time, displacement per unit time. Okay, so that is going to be L for displacement upon time. So T is going to be -1, M is going to be 0. M is going to be 0. So what is the dimension of speed? What is the dimension of speed? So speed is also distance per unit time. That means that the velocity and speed have the same units. Okay, the velocity and the speed have the same unit of meter per second. So this is going to be equal to m0 l t minus 1. Okay, because meter per second, so meter is the unit. Meter is the unit. Meter is the unit. Meter is the unit to the length, and second is the unit to the time. Okay, so the speed is going to be m0 l t minus 1. Okay, m0 l t minus 1. I hope it is fine to everyone. Now please understand this. So now you have come to notice this, that the speed and time, the speed and the speed and velocity have the same dimension. Do you agree or not? Sir, speed and velocity have the same dimension. Okay. Okay. So what we can conclude from here? So the physical quantities which have same units, have same dimensions, have same dimensions. Okay. Okay. So the physical quantities which have same units have the same dimensions. So sometimes these kind of questions are asked to you in the NEET examination, like which of the following questions would be like this, which of the following have the same dimension. So what you can think of, the quantities which have the same unit have the same dimension. Okay, okay, like work, energy, torque. If you see the unit of them, all have the same unit, Newton meter. So they have the same dimension. Okay, they have the same dimension, right? Okay, okay, so it is like this. Okay, so the physical quantities which have the same units have the same dimensions. Okay, now moving further, so we can have some more. So how many physical quantities we have done? 5. Okay, so if I forget the number, just pardon me. So we have one more, we can go for the acceleration. So what is the dimension of acceleration? And I hope that you are finding the dimensions of these while pausing the video. Okay. At times, and the live student can request me for to wait. Okay. Okay, so we have the acceleration. So acceleration is what? Change in velocity upon change in time. So change in velocity means okay, let's do one thing. So acceleration is change in velocity, no? Change in velocity, change in velocity upon change in time. Change in velocity upon change in time. So if the acceleration is change in velocity upon change in time, so basically it is final velocity minus initial velocity upon final time point minus initial time point. So I'll write it at delta t for time. Okay. Now, what is the unit of this velocity? Meter per second. What is the unit of it? This meter per second. So many students, what they do, they say that the unit of velocity, that is meter per second, minus unit of velocity meter per second. So this will become zero. Okay, so you don't do like this. Now, units and units are never cancelled out. So meter per second minus meter per second, it would become 0. On meter per second plus meter per second, it would become meter square per second square. Okay, don't do that silly mistake. So what is the unit of change in velocity? It is also meter per second. What is the unit of time? It is also second. So what is the unit of acceleration? The unit of acceleration is meter per second square. In the NEET examination, these kind of questions are also come, that what is the unit of this physical quantity? Okay, but I believe that as we move ahead in the journey of physics, you will get to know more and more physical quantities, and you will be able to then give the units of them. Okay, so that is going to happen in the matter of time. Okay, so many quantities we are going to see today till that you may or may not have seen before. Okay, okay, you might be in 11th class, you might be in 12th class, you might have forget some physical quantities, and as I said, I am starting the subject from the very basic. I believe that you don't know anything. Okay, and even I don't know anything. We are having this journey together. We are trying to learn the laws of physics, the world of physics. Okay, so what is going to be the dimension of this acceleration? So see, there is no term of kg, there is no term of mass. So can I write m0? Okay, m0. What is the dimension to the length? So it is having meters. So L1. What is the dimension to the time? So time is going to be -2. So m0 L1 t -2. Okay. Okay. So if I ask you what is the dimension of acceleration, what is the dimension of the acceleration? So the dimension of acceleration, will be 0 in mass. The dimension of acceleration will be 1 in length. The dimension of acceleration will be -2 in time. Okay. 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 So this is how you can find the dimension of many further units. So let us do some more. So after acceleration, we can have g. What is g? G is acceleration due to gravity. Acceleration due to gravity. So more or less, we treat it as also a constant, no? In the Earth atmosphere, that is 9.81 meter per second square. So this constant has unit. So this is not dimensionless. Now many people say, sir, constants are dimensionless. No, 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 no. Not all constants are dimensionless. The the constants are dimensionless if they do not have any unit. Okay. If g is acceleration due to gravity, so generally we use it as 9.81 meter per second square. Okay, sometimes for ease we also use it as 10 meter per second square. That is a different thing. But this constant has unit, so this is not dimensionless. And this is having the same unit as that of acceleration because it is acceleration only, no? Okay, so what is going to be the dimension to it? The dimension is going to be m0 L1 m0 L1 t minus 2. Okay, so the dimension of acceleration due to gravity is m0 L1 t minus 2. Okay, now coming to one very important quantity, that is the force. Okay, and I suggest you memorize. Okay, after we find the dimension of force, you must memorize the dimension of this force because this is very frequently used. Okay. Okay, so in future when we proceed, we will be using the dimension of force in many cases, because see, many physical quantities are derived from the force only, okay, like pressure, like stress, like energy, like work, like power. Okay, so these so many physical quantities are to some extent, depend upon the force. So this is a very frequently used quantity. That is why I suggest that you must memorize it. Okay, okay, so it will save time also, because see, in competitive examination, not only you must do the answer, you must do the question, you must solve the question, but you must solve them in a right frame of time. Okay, so what is this force? So sir, we know that Newton Baba told us force is equal to mass into acceleration. Okay, so what is going to be the unit of it? So the mass per kg, acceleration is meter per second square. Okay, so how can I represent it in terms of the fundamental units? Kg, we have a m, or right away you can write from here. Okay, so for mass we have the fundamental unit, that is m. Okay, then we have a, so a is lt minus 2, lt minus 2, we just have done that. Okay, we just have done that. Or from the unit itself you can write the dimensions of any quantity. So what is the dimension of force? So the dimension of force is mlt minus 2. Did I say right? No, sir, you haven't said right. Because dimensions are the powers to which the fundamental quantities or fundamental units are raised in order to express any physical quantity. Okay, so the dimension is not mlt minus 2. The dimension is 0 in m. The dimension is 1 in L, and the dimension is minus 2 in T. Okay. Okay. Although in some questions, or in most of the questions, they say which of the following is the correct dimension of force, and they write like this. Because if you write it like this, from here one can just by observation can say, okay, 1 for mass, 1 for length, and minus 2 for time. Okay. Okay. So I'll suggest you to memorize. Okay, this much you must memorize. Okay, so we have the force. Now please understand this. This kg meter per second square, we sometimes call it Newton also, na? Sir, we know that the unit of the force is Newton. Okay. Okay, so Newton is not a fundamental unit. Okay. Newton is what? Newton is, sir, it is the derived unit. Sir, how come it is a derived unit? So this is a derived unit. This is a derived unit because you see it is represented in terms of the fundamental units. Okay, so the units, there are some units which have some name but not fundamental units, because they consist of the fundamental units. So we have the Newton as kg meter per second square, mass, length, and time. Okay, so mass, length, and time are fundamental units, but Newton is made up of somewhat combination to these units. So Newton is the derived. Okay. Okay. So Newton unit is used frequently to represent the force, but Newton is kg meter per second square. I hope this is fine to everyone. Now moving ahead, so we had this force. Now we can go for the momentum. Okay. What is the formula for momentum? Sir, we don't know it yet. You haven't taught to us. No problem. Okay, I'll tell you the formula. Or like if I say momentum, you can Google it also, and we know everything. Okay, so momentum, if you don't know right now, don't worry. In future sessions, when you proceed with physics, you will come across each and every word of it. Okay, so momentum is mass into velocity. So what is going to be the dimension to it? So see, now without unit, I am writing it. I am doing it a little bit fast now. So m is for m. What is the fundamental unit of velocity, sir? It is lt minus 1, because we know it is displacement per unit time. Okay, so what is the unit of what is the dimension of momentum? So m0 l0 t minus 1. Okay, remember I'm saying like this, but the dimensions are the powers. Don't forget it. Don't forget it ever. Okay, this is quite a, because in questions also you see this, in many things you are seeing this representing like this, and then the student think this is the dimension. No, 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 no. Dimensions are the powers. Remember that. So momentum, then we have work. Okay, so what is going to be the dimension of the work? So dimension of the work is going to be, so we know work is force into displacement. Let's call it x. Okay. Okay, then don't tell me that's a displacement at the cos theta it is. But then further, we're going to see it further. We are here interested in the formula. Literally, let me write dx cos theta. Okay, many students will be happy to see this. Okay, now does cos theta have any dimension? No, sir. This is an angle. Okay, so if theta has got any value, when you put this theta into cos, you will get a number. No? So this cos theta, sin theta, tan theta, all these have no dimensions. All these have no dimensions, right? Okay, so now what is going to be the dimension? So what is going to be the unit? So sir, force is Newton. This is going to be meter, or I can write. So force is mass into acceleration, that is kg meter per second square, and we have this meter, so we can write kg meter square per second square, and we popularly call it, what is the unit of work if I ask you? So you would say that the unit of work is joule. Okay, okay, so again joule is a derived unit because it is formed from the fundamental units of mass, length and time. Okay, okay, so how can we have it? How can we have it? So we can have m. Okay, this is meter square, that is L square, and that is T minus 2. Okay, so this is the dimensions of the work. Okay, so from this you can find the dimensions. Okay, I hope I have cleared my point. Okay, now we have, so how many were there? 10. So now work, we can go for energy. Okay, so what is the unit of energy? So this is also Newton meter, no? Because work is a form of energy, we all know. Okay, so how work and energy are different from each other? So there is a difference. There is a lot of difference actually. I'll tell you in thermodynamics. Don't worry. So they describe something different, though they represent the same thing. We'll talk about it. But certainly, sir, they have the same unit. This is we are sure about, isn't it? Work is Newton meter, sir. Energy is also Newton meter. So what is the fundamental? How we can represent it in terms of fundamental quantities? So again, sir, it is going to be m l square t minus 2. Okay, and more quickly how you can do it, so you memorize the dimension of the force, that is m l t minus 2, force into length, so length is l, so it will become m l square t minus 2. So energy, work have the same units. Okay, so they have the same dimension. What we have learned, sir, those physical quantities which have the same units, the physical quantities which have the same units have the same dimension, and this is valid for all types of energy. Okay, remember this. Okay, all types of energy. Okay, so what are all types of energy that we frequently see? All types of energy. Okay, so all types of energy, like kinetic energy we have, potential energy we have, heat energy we have. Okay, so so many forms of energy. So if you see any formula which have some sort of energy, okay, okay, like any formula, any given formula, okay, okay. So what you can do, you can use this unit, this fundamental, use these dimensions to express that energy. So all types of energy, all forms of energy have the same dimensions because again they have the same unit. Okay, yeah, I hope that technical issue is sorted. Some technical issue came up, no problem. So power is what? Power is work per unit time. Okay. We know that the power is work per unit time. So what is going to be the dimension to it? So the work is m, unit of the work, or the dimension of the work is m L2 t minus 2. Okay, and what is the dimension, or how we can represent this time? So this is like this. Okay, so what is going to be the fundamental dimension of power? So m L2 t minus 2, t minus 3. Okay, so dimension the fundamental dimension of this power is ml2. Sorry, the dimensions of this power is ml2 t minus 3. Similarly, we can have the dimension of impulse. Okay, So all these you are going to see as the previous year question. So I am going to get you solve so many things. Okay. So what is impulse? Impulse is force into time, right? Impulse is force into change in time. Okay. Now change in time, what is the unit of change in time? So second minus second becomes zero. It is unitless. Don't say like that. Okay. Second minus second will be second. So the unit of the change in time is also going to be the second. So what is this force? What is the fundamental what is the dimension of this impulse? So what is the dimension of this force? So sir, it is m l t minus 2. It is m l t minus 2, and for time we have t. For time we have t. So we are going to have it as m l t minus 1. m l t minus 1. I hope it is fine to everyone. Okay, so what is the dimension to the impulse? The dimension to the impulse is ml t minus 1. I hope it is clear to everyone. Okay, I hope it is clear to everyone. Now, can you suggest me some more physical quantities? Okay, so let's go to rotational. Okay, so we have angular velocity. We have angular velocity. So what is angular velocity? What is angular velocity? So angular velocity is change in angular displacement upon time. Okay, or we can write it, so we know now v is equal to r omega. This is also, you might have aware of this formula. So v is equal to r omega, that is v perpendicular, upon r. Okay, remember this v, when we say v is equal to r omega, this v is the perpendicular quantity. This v is the perpendicular quantity. So from here you can get the dimension of it. So what is the dimension of this velocity? This is lt minus 1. Okay, or you can do the bracket thing, or you can make the bracket in the last, whatever you prefer. Okay, then we have this l. So basically what is the dimension of this angular velocity? It is going to be m0 l0 t minus 1. m0 l0 t minus 1. Okay, okay, or you can do it by the unit also. Sir, we very well aware that the unit of the angular velocity is radian per second. Now radian is dimensionless because it is the angle. Remember, angles are the supplementary quantities which have the units but no dimension. Okay, which have the units but it has no dimension, right? So angular velocity is m0 l0 t minus 1. Okay, that is the dimension. Okay, okay. Now moving ahead, so we have the frequency also. Okay, what is the formula of frequency? Anyone? The formula of frequency is 1 upon time period. Okay, 1 upon time period. So what is going to be the unit to it? What is going to be the unit to it? So it is going to be 1 by second. Okay, 1 by second, or you can get the fundamental dimension right away from here. So we have 0 dimension to the mass, we have 0 dimension to the length, we have -1 dimension to the time. Okay, this is going to be the dimension of frequency. Then we can have the angular frequency. Okay, so how many will become? So 12, 13, 14. This is 15. This is 15, not 16. Okay, so I forget to number. So this is 16 also. So now let's come to the 16 one. So we can have the angular frequency. Angular frequency. So angular frequency is what? Angular frequency is what? So basically, angular frequency, we normally represent it as omega. Angular velocity is also generally represented as omega. So what is this angular frequency? So it is 2 pi f. Okay. Okay, so if you have done this simple harmonic motion or vibration kind of the chapters, or if you have any idea about that, so there we use this frequency. Okay, okay, so 1 by second is also, this is known as hertz. Okay, you might have read it. Okay, okay, so this is 2 pi f. This is 2 pi f. So what is going to be the unit of it? So again, 2 pi is a number. It is a constant number. So it has no dimension. So angular frequency is going to have the unit of the frequency itself. Okay. So what is going to be? So it is going to be m0 L0 T0, M0 L0, sorry, T minus 1. Okay, I think you can't see this what I'm writing here because you are watching my face. So it is going to be M0 L0 T minus 1. So what is going to be the dimension to the angular frequency? The dimension to the angular frequency is going to be 0 in M, okay, 0 in mass, 0 in length, and minus 1 in time, and minus 1 in time. Okay, then we have the angular acceleration. Okay, so many, as I said, so many physical quantities we have. There is no end to it. Okay, so what we are trying to do, we are trying to do as much as possible here. So angular acceleration. So what is going to be the dimension to the angular acceleration? So the angular acceleration, it is the rate of change of angular velocity. It is the rate of change of angular velocity. So you can see it in the unit of radian per second square, obviously. Okay, so angular velocity has the unit of radian per second, and per unit time, time has the unit of second. Okay, so angular acceleration is going to have the unit of radian per second square. Now, radian is dimensionless. Okay, so can we write the dimension to it? So it is going to be m0. It is going to be m0. It is going to be l0. It is going to be t minus 2. So what is the fundamental? What is the fundamental? What is the dimension to angular acceleration? It is going to be m0 l0 t minus 2. Okay, okay, then we have this torque. Okay, let's do for the torque. So what is this torque? So torque is basically force into perpendicular distance. No, force into perpendicular distance. Okay, so what is going to be the unit to it? What is going to be the unit to it? So the unit is going to be Newton meter. Okay, force is Newton and the perpendicular distance is meter. Okay, so what is going to be the fundamental? What is going to be the dimension? So sir, mlt minus 2, mlt minus 2 is the dimension to force, and we have some L multiplied to it because the dimension of the distance is L, so it is going to be ml square t minus 2, and again you can observe that it is having the same dimension as that of the work and that of the energy, because as I said, work, energy, torque, they all have the same unit, and the quantities having the same unit must have the same dimension. Okay, they have the same dimension. Now if we see, let's go for mass moment of inertia. Mass moment of inertia. So what is going to be the dimension of mass moment of inertia? So what is mass moment of inertia? It is mk square. What is k? K is the radius of gyration. Okay, so see, by learning this chapter, this is very beneficial, because see, before even, so you are going to see this mass moment of inertia when we are going to study the rotation of the particle or rotational mechanics. Okay, okay, but right now you can have a rough view of these formulas. Okay, and if you start finding the dimension, when you start solving the question, even before you reach to that chapter, there are some formulas that are always in your mind, that is already there in your mind, so it is going to be helpful to you. It is going to be helpful to you, okay, in understanding that chapter. Now get me the dimension. Now get me the dimension to mass moment of inertia. Yeah, just had some H2O. Okay. So now, mass moment of inertia. So we have mk square. What is going to be the fundamental dimension to it? So it is going to be m. Okay, and this is your radius, that is length. So ml is square. So what is the fundament? What is the dimension to the mass moment of inertia? The dimension to the mass moment of inertia is ml square. That is 0 in mass. That is 2 in L, that is 2 in L, and 0 in time. We can write like this also. Okay, we can write like this also. Okay, okay. Now we have something. Okay, so we can find. Let's do some more. So what is the number? We have reached to 19. Okay, now 20. So 20 we can have angular momentum. 20 we can have angular momentum. So what is this angular momentum? So angular momentum, we know it is mvr sine theta. Okay, so if we when we see the formula, we'll see mvr sine theta. Okay, okay. So basically mv is what? It is linear momentum. It is linear momentum. Okay, okay. So for this, what is this? What is this? So we can write the unit here. Sine theta is dimensionless because this is obviously an angle. So m is mass, velocity is L t minus 1, L t minus 1, and R is L. R is L. Okay, so this is going to be m L square, m L square, okay, t minus 1. M L square t minus 1. Okay, so what is the dimension to the angular momentum again? So we can have the dimension of angular momentum here. Now let's do some quantities. Okay, so see, there are n number of quantities. I might have missed some of the physical quantities. That is obvious. I can't cover all the physical quantity. I'm just trying to tell you the way that if you know the formula of some physical quantity, if you know the unit of some physical quantity, how can you get the dimension of that particular? Okay, now moving ahead. So we have this stress. Okay, now let's talk about the mechanics of solids part. Okay, or properties of solid. So what is the stress? So when you go to that chapter, and you will see that stress is force upon area. Okay, stress is force upon area. So force upon area, that is, what is the unit? So unit is going to be, the unit of the force is Newton, the unit of area is Newton, the unit of area is meter square. So what is going to be the dimension? So the dimension is going to be ml, okay, ml t minus 2. This is the dimension. This is the dimension. So you can use this bracket thing. Okay, some students say, why sir we are using the bracket again? This is the right representation. Okay, okay. Some of them don't do with the bracket. They get irritated with the bracket. So that is fine. This is how you want, because ultimately you need to get to the correct answer. That may be a fine approach. That I am not against it. But this is the right representation. So I am doing like this at sometimes when I do my practice, or when I do my learning, or when I solve myself questions. I don't do this bracket thing often. Okay, but I don't recommend you to do that. Okay, so this is m l minus 1 and t minus 2 and t minus 2. So this is going to be the fundamental, this is going to be the dimension to the stress. This is going to be the dimension to the stress. Now there are some more quantities. Let's go for in the solids. What are the more quantities? So strain we have, right? What is this strain? So strain is change in length upon original length. What is the strain, guys? Strain is change in length. Strain is change in length upon the original length. Upon the original length. Upon the original length. So what is the unit to the change in length? So this is meter only. No, difference or addition. When two physical quantities are added, their unit is going to remain the same. When two physical quantities are subtracted, again their unit is going to be the same. So when we do the subtraction, units are not subtracted, guys. Okay, so this is, what is the unit? This is meter, this is also meter, so this is cancel out. So this is going to be unitless or dimensionless. So what is the dimension to this strain? This is going to be m0, l0, t0. So you can do it in any way that you want, from unit, from formula, whatever feels right to you, or whatever comes to your mind first. Okay, okay. Now after strain we have Young's modulus. Okay, we have Young's modulus. So for every material, this Young's modulus is a constant. Okay, like for steel, it is 200 GPa. For cast iron, it is nearly 100 GPa. For aluminium, it is nearly 75 GPa. So for any other material, it could be different. Okay, but for a material, it is deemed to be constant. Okay, so this is a constant. Will it be dimensionless? No, sir. It is not going to dimensionless, because when you are going to see the formula of the Young's modulus, you would say that this is going to be equal to stress upon strain. This is the normal representation to strain. This is the normal representation to stress, sigma, okay, and epsilon. So Young's modulus is stress by strain. Is stress by strain. So strain is dimensionless. So Young's modulus is going to enjoy the dimension of the stress. And what is the dimension to stress we just have seen? This is M L minus 1, L minus 1, T minus 2, T minus 2. Now, if I ask you what is the dimension to pressure, or sir, we know that the pressure is also force upon area. When pressure is also force upon area, that means it is having the same unit. It is having the same unit as that of the stress. And since these two physical quantities enjoy the same unit, if these two physical quantities enjoy the same unit, they have the same dimensions. Okay, okay. Okay, so when we learn properties of solid, will be coming across this Young's modulus, stress, strain. You will see that how they are related. The stress and strain are related. How they are related using the Hooke's law, very famous Hooke's law. Okay, we'll come to that when the time comes. Okay, now we have. Let's come to the properties of fluids. So we have surface tension. Okay, surface tension. Okay, what is the surface tension? It is the force per unit length. Okay, you are going to see it in the fluid. Okay, okay, so you might have heard, okay, like this water, why they form a spherical shape when there is no gravity in vacuum. Okay, okay, so this bubbles, this water droplets form the shape of a sphere because of this property of surface tension. We'll be discussing it in a very great manner, in a good manner. Okay, don't worry about it. So this is one term. So right now, please remember, I'm not expecting you that you memorize this formula right away, and neither I expect that you already knew this form. But I know that with your journey to the physics, or with our journey in the physics, we are going to see these formulas in the upcoming chapters. Okay, so we are having their dimensions beforehand. Okay, okay, so with every chapter that you learn, you can have the dimension of each of the physical quantities, like this one. So this is force per unit length. So very simply we can write what is the dimension to the force. So we have memorized it, ml t minus 2, ml t minus 2. Sir, what is the dimension to this length? Sir, this is L. So basically, what is the dimension to the surface tension will become? Sir, it is becoming M. We can write L0 because L is now become 0. It has no power. And then T minus 2. Okay, so basically, sometimes we say it is MT minus 2. Okay. Okay, remember in general we represent any dimension in terms of MLT, though we can have them represented in terms of temperature, current, candela, mole, etc. So if I ask you that what is the dimension of surface tension in current, in electric current, what would be your answer? What would be your answer? You would say, sir, obviously, sir, it is 0. Obviously, sir, it is going to be 0. Okay. Okay, now moving ahead. Now we have done some. So let's go to the 12th physics. Okay, sir, 12th physics. Oh, 12th physics. So can you suggest me some terms, the live student? Let me think of. So let's say electric charge. Okay, electric charge. Okay, so what is the formula to electric charge? So it is I into delta T. Okay, that is current into change in time, and we represent it generally by Q. Okay, okay, and now see, you don't have to get trapped in the symbols also. See, Q is also used for heat. Okay, okay, Q is also used in general for heat also. It is also used for charge. So we are talking about the dimension. So what is the dimension to A? Sorry, what is the dimension to I? So it is current, so we can write it at ampere. What is the dimension to delta T? So it is T. Okay. Okay, so we can have the dimension of mass, it is 0. Dimension to L, it is 0. So basically, this is the dimension to electric charge. Okay, this is the dimension to electric charge. I hope it is fine to everyone. Okay, so when I don't write something, it is basically 1. No. Okay, don't forget that. Okay, so many places I haven't like for here M. Okay, so obviously it is 1 now. When I have written something, it is 1. When you written X, just you have written X. So what is the power to X? The power to X is 1, obviously. So we all know it, no? Nothing to worry about. Okay. Okay, so sometimes it is written as M0, L0, T1A. Just to follow the sequence, and this is also fine. Okay. Okay, let's have some more quantity from the 12th physics. So what we can have potential, electric potential. Electric potential. Okay. Can you tell me what is the formula to electric potential? Anyone? What is the formula to electric potential? So the formula to electric potential is electric energy upon charge, that is W by Q. That is W by Q, and we generally represent it as V. Okay, so this is form of energy, and this is your charge. So what is going to be the fundamental dimension? So energy, what is the dimension to the energy? It is mL2 T minus 2. I said, how come? Force we already have memorized, no? We have used this so many times. I think if you watch this whole video, after you must have memorized this by already by this point of time. If you have watched the whole video, you must have memorized the dimension of the force. What is the dimension to the charge? So the dimension to the charge is A. Okay, so what it is going to become? It is going to become M L2 T minus 2 M L2 T minus 2 A minus 1. I hope it is fine to everyone. Okay, so this is the dimension to the potential. This is the dimension to, oh sorry, charge is A into T, right? Okay, charge we just have found now, A and T. So this is must be T minus 3. Okay, this must be T minus 3. Okay, what else? What else? What else? So we can have electric resistance. We can have the resistance. Okay, we can go for the resistance. Okay, just 1 second. I have some technical issue. Electric resistance. So what is this electric resistance? So sir, if we know the formula of electric resistance, or if we know the unit of the electric resistance, definitely we are going to know the dimension of this electric resistance. So what is the dimension to this electric resistance? So it is change in potential upon current. Okay, yeah, that means delta V. So let it be V upon I. No worry. Okay, so we must have memorized V upon V is equal to IR. No, or V upon I. Okay, right now, as I said, I don't expect you to memorize the formulas, or you already know the formula. I'm not expecting that. Okay, so what is the dimension to this V? So it is M. Okay, it is L square T minus 3, L square T minus 3, A minus 1. A minus 1 upon I. So I, for I, it is A. Okay, so what is the dimension to the electric resistance? So this is going to be M. This is going to be M L square T minus 3, T minus 3, and A minus 2. A minus 2. Okay. Okay, so let's move to, we can have some more formulas. See, I hope you have understood the point till now. Okay. Okay, we can do as many as you want. We can have the dimension of the capacitance. What is the problem? Capacitance. And what is the formula to capacitance? What is the formula to capacitance? So we represent it like C, and Q is equal to CV. Okay, Q is equal to CV. So capacitance is equal to Q upon V. Q is charge and V is potential. difference. So what is the dimension to the charge? So it is 80. Okay, and what is the dimension? What is the dimension to this potential sub m L2 t minus 3 a minus 1? No need to memorize all this, no. Otherwise, the only chapter you will know in physics is this. Okay, you can't memorize everything, na? Can you? Can you memorize everything? No, sir. Okay, if you are able to memorize each and everything, then there is no issue at all. But you cannot memorize everything. Okay, so there is absolutely no need of memorizing of the dimension of each. Okay, force we can do because it is very frequently used. Okay, and basically, if we know the dimension of the force, we can, in our mind only, without writing anything in the copy or something, we can get the dimension of many quantities like pressure, stress, Young's modulus, energy, power, right? Work, torque, momentum, okay, like that. Okay, so from here we can get the dimension of the capacitance as well. Okay, what it is going to be? It is going to be m minus 1, L minus 2, T4, okay, and A minus 1 going to the numerator, it is plus 2. Okay, it is going to, oh, it goes in my video. So I'm writing it here. Okay, A2. So this is together. Okay, I have written it in downward because of my video you can't see this, right? Okay, so sometimes in flow this kind of thing happens. Okay, okay. So if we go for the thermodynamics, okay, so how many we have done till yet? 28 we have done. So you can consider it at 28 question, not 29. So 29, that is the temperature gradient. That is the temperature gradient. Okay, so what is going to be the dimension to the temperature gradient if I ask you? So sir, the temperature gradient will have the dimension of delta T by L. Delta T by L. So delta T by L, what is the dimension to the delta T? It is going to be the temperature. Temperature difference unit is temperature only. So you can write as K, and this is the length. Okay, so what is temperature gradient? So change in temperature per unit length. Okay, change in temperature per unit length. Okay, so K by L. So this is going to be M0, L0, sorry, L minus 1, not 0, L minus 1, T0, and K1. Okay, K1. Okay, okay. So this is going to be the dimension of the fundamental dimension of the temperature gradient. Okay, and again I am telling you that the dimensions are the powers to which the fundamental units are raised to express any derived physical quantity. Okay, derived physical quantity. Okay, okay. Now let us get the dimensions of some of the constants that we frequently see in the physics, okay, or in the chapters of physics. So basically the dimensions of some constant are dimensions of some constant. So what is going to be the dimension of some constant? So the dimension of some constants are going to be dimensions of some constants are going to be, so just help me with some constants. Refractive index, what is refractive index? So many of you might be already in preparation, okay, although I am not considering that. Refractive index, so what is going to be the formula of refractive index? So it is what? It is the speed of light in, what is refractive index? So speed of light in a vacuum, speed of light in vacuum, okay, upon speed of light in medium, upon speed of light in medium. So basically in the numerator we have speed, in the denominator we have speed. So speed and speed, the units are going to be cancel out. So this is going to be unitless. That means it is going to be dimensionless, isn't it? Dimensionless. Sir, how come? Oh my God. So the unit of this is speed. So is speed of light in vacuum. So it is going to have the unit of meter per second. Is speed of light in medium. It is again going to be in meter per second. So meter per second will be cancelled out. And this is going to be your dimension. This is going to be your dimension. Okay. Okay. So I have told you about, so this is okay, so this constant is dimensionless because it has no unit. Now let's take the universal gravitational constant. Universal gravitational constant. Universal gravitational constant. So what is going to be the universal gravitational constant? How you can get that? So what is the formula? What is the formula? So G F is equal to G m1 m2 upon r square. Okay, I hope we know that. Okay, if you don't know that, that's okay. So here F is the force. F is the force. Okay, m1 m2 are masses. Okay, are masses, and r square is going to be the radius. R is going to be the distance. Basically, it is the distance between the masses. So basically, it is some sort of a distance. Actually, it is distance between the masses. Oh my God, sir, we haven't seen this formula yet. Okay, don't worry. I am giving you the formula. I am giving you the formula. You just give me the dimension. Okay, okay. I give you the formula. You give me the dimension. Okay, right. So F is equal to G m1 m2 upon r square. So from here we can get the unit of the G. G is a constant. Okay. But though it is having some units, so how we can do that? Please observe how can we do that. No worries at all. So sir, we can write G is equal to F into r square upon m1 m2. F r square upon m1 m2. So we can write this straight away. So, sir, we memorized the dimension of this force. So, this is mlt minus 2, mlt minus 2. So, the dimension of this r square, obviously, it is going to be l square. And dimension of this m1, m2, this is going to be m, this is going to be m. So, basically, it is going to become m minus 1, it is going to become m minus 1. Okay, it is going to become m minus 1, it is going to become l cube, it is going to become t minus 2. It is going to become t minus 2. Okay, okay. Now please observe. So as I stated earlier, not all the constants are dimensionless. Okay, not all the not all the constants are dimensionless. Okay, not all the constants are dimensionless. Okay, so universal constant of gravitation. Okay, this universal gravitation constant is not a dimensionless, constant because it has units. So what we learned, so the constant which have the unit, the constant which has the units are not dimensionless. So can you name me any few more? So what I said Planck's constant. Okay, now let us get the dimension of the Planck's constant. Okay, let us get the dimension of the Planck's constant. So how can we get the dimension of Planck constant? Sir, if we know the formula, we can get the dimension, right? So I'm going to give you the formula. E is equal to hf, where h is the Planck constant, E is the energy, and F is the frequency. F is the frequency. So we can write H is equal to E by F, right? Okay, H is equal to E by F. Okay, so now we can reduce it to the dimensions. So we can write So what is the dimension to the energy? So the dimension to the force is mlt minus 2. Force multiplied with length is the energy. So we can write ml square t minus 2, ml square t minus 2. And what is the dimension of the frequency? So it is t minus 1. It is t minus 1. So sir, this is going to become m L2 ml2 t minus 1. This is going to become ml2 t minus 1. I hope it is fine to everyone. So again, as I said, some constants are not dimensional. Okay, okay, okay. now, so which other constant they ask for? Okay, so in need they have asked of the Boltzmann constant. The Boltzmann constant. Okay. So what is the dimension of this Boltzmann constant? Can anyone in the live please tell me? I can see that some students are live here. So what is the dimensions of this Boltzmann constant? Anyone? Anyone? So this is PV is equal to KT. This is PV is equal to KT. So if you don't know the formula, this is the formula. P is the pressure. P is the pressure. Okay. V is the volume. V is the volume. And T is the temperature. T is the temperature. So again we can have that. Again we can have them. So we can write K is equal to PV upon T. K is equal to PV upon T. So what is the dimension to the pressure? So mLT minus 2 upon ml upon L square. Okay, you can think in your mind also, right? So because we have to raise the speed also, no? So pressure is equal to force upon area. So force is mLT minus 2 upon area, that is L square. So L upon L square, that will become mL minus 1. That will become mL minus 1. Okay, and this is going to be T minus 2. Okay, this is going to be volume, that is L3. That is L3 upon temperature. So we can write it as, so K. See, here Boltzmann constant generally is represented in K. Now what is advisable? What is smart to do? So this thing is smart, na? If we use T as theta, because otherwise we may get confused in K and K. Okay, so definitely then we must be using this theta. So what is the unit of it? What is the dimension going to become? So it is going to become m L2 L square T minus 2 m L square T minus 2 and theta minus 1. So theta represents the fundamental unit of temperature here. So we can have many there are many other constants as well. So we can have this coefficient of, we can have here the coefficient of dynamic viscosity. Okay, again a term we'll see to use in the fluid. Okay, that is the properties of fluid, as you say. Okay, I say it as mechanics of fluid. Okay, so we have coefficient of dynamic viscosity. So what is the formula? From which formula this coefficient of dynamic viscosity comes out to be? So from the Newton's law of viscosity. From the Newton's law of viscosity, the shear stress is equal to mu du by dy, that is change in velocity upon a clearance, that is a change of distance, you may say, for the time being. Okay, so this mu, or I may write mu because my mu is very bad. Okay, I am unable to make it correctly. So I'll show it by, no worries. So you can show it by mu, you can show it by eta, anything that you want. Okay, so what is the dimension to it? So this is shear stress. Tau is shear stress here. This is your shear stress. Okay, this is your change in velocity. This is your change in velocity. Okay, and this is your change in length. This is your change in length. Okay, this is your change in length. So shear stress is equal to coefficient of dynamic viscosity into du by dy. Okay, so from here we can write the dimension of it. So the shear stress. So again force upon area. So you can think. So we just have then the for the pressure, no? So this is going to be, let me write it. So m L T minus 2. So M L minus 1, T minus 2. We just have done it. Na? Stress, pressure, dimensionally, they are all the same thing. Okay, divided by the change in velocity. So what is the dimension to the change in velocity? So it is going to be the dimension of velocity, that is LT minus 1. And what is the change in length? So this is going to be L. This is going to be L. Okay, so it will become M L minus 1. Okay, it will become M uh, so MLT minus 1. Okay, sorry. Some mistake has happened. So see, this velocity is going to be in denominator and this dy is going to be in the numerator now. Okay. Okay, so this is going to be, see, such mistakes are to be avoided. Okay, so sometimes we get this. Okay, so we have what it is going to become. So L minus 1, that will become 0, and this is going to be, so you don't have to hurry to anything now. As I hurried here, you don't have to do that. Okay, and this will become T minus 1. This will become T minus 1. So this is going to be become ML minus 1 T minus 1. Okay. Okay, so these are the units to various constants. So you have seen that some constants are dimensionless, because when the constant has no unit, it is going to be dimensionless. When the constant has some unit, like the coefficient of dynamic viscosity, Planck constant, Boltzmann constant, okay, universal coefficient of gravitation. So all these are the constant which have some dimension. Okay, because they have some units. So the constant, not all the constants are dimensionless, but the constants which do not have the units, it is better to say like that, the constant that do not have some unit are that dimensionless. So let's see one more. Okay, so let's take it from some thermal side. So we can do for molar specific heat capacity. Molar specific heat capacity. So I think after you see this session, how many questions we have done? So we have this so we have done 6 for constants, and how many? Okay, 29 and 6, so that is 35 dimensions we have calculated today. We are on our 35th. So what is this? So Q is equal to NC delta T. Okay. Okay, so here Q is the energy. It is the heat energy. N is the moles. Okay. C is the molar specific heat. Temperature difference is the Kelvin. Temperature difference is the Kelvin. So heat energy is M L square T minus 2, M L square T minus 2. Okay. Okay, so we need to get this C. So this is moles. So we can take it to the denominator and we can represent it as the fundamental dimension of mole, right? Okay. Okay, and this delta T, so we can have it represented as K or theta, whatever we wish to have. Now from here, obviously we can get, so we will get M L square T minus 2, M L square T minus 2, T minus 2, mole minus 1, okay, mole minus 1, and K minus 1. K minus 1. So this is going to be the dimension to the molar specific heat. Okay, molar specific heat. So in the same way, you can get the dimension of anything. Okay, you will see some neat questions like get the dimension of the thermal conductivity. So if you know the formula of thermal conductivity, you can get the dimension of the thermal conductivity as well. So if you know the formula of any quantity, if you know the unit of any quantity, you can get the dimension of that quantity very, very easily in just few steps as we have learned here. Okay. Okay, so I hope guys, this session is helpful to you. So in this session, we have found the dimension to many physical quantities, approximately 35 we have done today. Okay, okay, so I'll keep it to this session to this point in this session, and in the next session we will be talking about the principle of dimensional homogeneity. Okay. So as I said, using these dimensions, you can check whether an equation is correct or incorrect. Okay. So we are going to do that. Further, we are going to find the dimensions of many parts of the equation. So the next session is going to be very exciting, very productive. And see, as I promised you before, so by watching these sessions, you don't have to do questions much more because we are doing so many questions in the class itself. So rather than focusing on the theory, I could tell you so much theory also, but rather than focusing more on theory, we are focusing more on numericals. As today we have done so many numericals, in the upcoming sessions also we'll focus more on numerical, we'll solve more and more problems. Okay. Okay, so guys, to this point, I'll keep it to this point in this session. And before I go, I request you to please like the video, please subscribe the channel, and please do come live from the upcoming sessions as well. So with this, thank you very much. Have a great day ahead, and best of